Assalamualaikum. Hi. In this video, I and my teammate are going to talk about gas chromatography.
Assalamualaikum. Now I'm going to introduce the team members. First we have me, Nur Yasmin Irdina binti Bashahrudin. Next we have Nur Husna binti Abdullah, and lastly we have Nur Marsya Aimee binti Marzimi.
Now, we are going to look at the objective of this experiment. This experiment was run to determine the retention time of N-butanol and 2-propanol. Next is also to determine the effect of temperature on retention time and resolution. We also wanted to identify the components present in a standard mixture based on the retention time and also to identify the component present in an unknown sample.
So next, we have introductions. Gas chromatography or GC is an analytical technique that we use to separate and identify volatile and semi-volatile compounds in a mixture. In GC, separations happens when the sample is carried by an inert gas through a column that contains a stationary phase. Different compounds interact differently with the columns, so they come out at different times. In this experiment, we use GC to analyze both a mixture and unknown samples. The separation is based on retention time, or RT, which depends on factors such as boiling point, interaction with the stationary phase, and the column temperature. By comparing the retention time of the unknown sample with known standards, we can qualitatively identify the unknown compound. We also studied how column temperature affects retention time and peak resolutions, because these factors are important to obtain good separations and accurate identifications in GC analysis.
Now, let's look at the how behind the science. This diagram illustrates the methodology and instrumentation of a gas chromatography system, which allows us to separate and also analyze complex mixtures with high precision. Everything begins with the carrier gas, which acts as our mobile phase. Commonly, we use inert gas like helium, nitrogen, or hydrogen to transport the vaporized sample through the system. To ensure the results are consistent and reproducible, we use a gas flow regulator to strictly control the flow rate and also pressure. Next, the sample enters through the injector pod. This is where the sample is introduced into the GC system. Because this area is kept at a high temperature, the sample is rapidly vaporized so it can begin its journey through the column. The actual separation happens here, in the column, which is housed inside a temperature-controlled oven. The oven is crucial because its temperature affects retention time, resolution, and overall separation efficiency. The column contains the stationary phase, which is responsible for separating components based on their individual volatility and how they interact with that stationary phase. Once the separated components exit the column, they pass through a detector. Common examples include FID, TCD, or ECD. The detector converts the chemical signal into an electrical signal, where the intensity you see is directly proportional to the amount of the compound present. Any excess gas or eluted sample is safely removed as waste. Finally, the computer or data analysis system records this signal, and the output is displayed as a chromatogram, which we use for both identification and quantification of the substances in our original sample.
Okay, on this slide, we can see the retention times of different compounds obtained from our gas chromatography experiment. First, we test the standard mixture at 70 degrees Celsius, which contains 2-propanol and N-butanol. Their retention times were 3.011 minutes for 2-propanol and 3.582 minutes for N-butanol. Next, we analyze pure 2-propanol and pure N-butanol separately at the same temperature. 2-propanol had a retention time of 3.025 minutes and N-butanol was 3.643 minutes. We also test an unknown sample at 70 degrees Celsius, and the results show retention times of 3.019 minutes for 2-propanols and 2.608 minutes for N-butanol. This indicates that the unknown contains both compounds but in slightly different proportions compared to the standards. Finally, we observe how increasing the column temperature affects the retention times. At 100 degrees Celsius, the standard mixture showed lower retention times of 2.681 minutes for 2-propanol and 2.870 minutes for N-butanol. When the temperature was increased further to 140 degrees Celsius, the retention times decreased even more to 2.420 minutes for 2-propanol and 2.497 minutes for N-butanol. This shows that higher temperature decrease the retention times of compound in gas chromatography, which is consistent with the principles that compounds travel faster through the column at higher temperature.
Next, we have chromatograms of standard mixture in 70 degrees Celsius in the left side and chromatograms of 2-propanols in the right side. On this slide, also have chromatograms. On the left side, we have chromatograms of N-butanol. On the right side, we have chromatograms of unknown sample. Okay, for the last slide of results, we have on the left side a standard mixture in 100 degrees Celsius, and the right side we have standard mixture in 140 degrees Celsius.
For this discussion, to determine which peak in the unknown chromatogram corresponds to each compound in the standard mixture, retention times were compared under the same GC conditions. So in this experiment at 70 degrees Celsius, the unknown sample showed a peak at 3.019 minutes, which is very close to the retention time of 2-propanol in the standard mixture, which is about 3.02 minutes. Since the retention times are almost identical and the analysis was performed under the same conditions, the peak in the unknown chromatogram was assigned to 2-propanol. When the column temperature was increased, the retention time decreased because the compounds traveled faster through the column. However, when the column temperature was reduced, the retention time increased and the peaks were better separated, resulting in improved resolutions. At higher temperature, peaks elute closer together, which reduced peak resolutions.
In this experiment, gas chromatography was successfully used, an effective analytical technique to separate and analyze volatile compounds. The retention time of N-butanol and 2-propanol were determined, demonstrating that each compound has a characteristic retention time under fixed operating conditions. This confirmed that retention time can be used as a reliable parameter for compound identification. The effect of temperature on retention time and resolution was also observed. As the column temperature increased, the retention time of both compounds decreased due to faster vapor movement through the column. However, higher temperature lead to reduced resolution, highlighting the need for optimal temperature selection to achieve good separation. Furthermore, the components in a standard mixture were successfully identified by comparing their retention time with known values. Using the same approach, the components present in the unknown sample were identified. proving the usefulness of gas chromatography in qualitative analysis. Overall, this experiment demonstrates that gas chromatography is a powerful and reliable technique for separation, identification, and analysis of volatile organic compounds based on their retention behavior.
That's all from us. Thank you.